Hello there, my dear students. In this lecture video, I'll be discussing about uh, the another important element of a circuit. So that would be what we call electromotive force, the concept of electromotive force. So at this point in time, if we have a DC circuit here, that's very simple, no? So you know that this is the symbol for a battery, for example. Yan. And then let's say you have a resistor here. So we have a very simple series circuit. Okay, tinanggal niya. Lagyan natin ng resistor R here. Yan, positive, negative. So in the previous 3 or 4 videos, we've already discussed the concept of current, no? So we have current as the time derivative of electric charges. And then we also know that it's affected by the kind of material, no, the number of free electrons per cubic meter. And then to have the charge here, the cross-section area of your wire, and then the drift velocity. And then we also studied about the characteristics of our wire, wherein we had learned about resistivity, which is a characteristic of your wire as the ratio of electric field to current density, where current density, of course, is the ratio of current to cross-section area of your wire. And then resistance, still another characteristic of our wire where your charges flow through. So we have rho and then the length over the cross-section area. So in this video, we'll be talking about the physical quantity that somehow makes this current possible. Without it, there can be no flow of charge in our wire. So, and that is what we call the electromotive force, okay, or the EMF. Or our symbol is like this cursive English letter E, but it's actually a Greek letter, no? Ayan. So, let's say, for example, we have a piece of conductor that is not that's not involved or connected in a closed circuit. So it's just uh, let's say a piece of wire. Ayan. And then let's just say, for example, there's a certain mechanism wherein within the wire, there is a certain electric field, no, from this point to that direction. Let's call this as electric field 1. And take note that your wire is not connected to a closed circuit, no? So it's just independent, not connected to a complete circuit. But there is a mechanism where initially there's electric field within the wire. So you've learned that if there's electric field in the conductor here that goes to the right, then the positive charges, yung conventional current natin, will go to with the direction of the electric force. So there's electric force here that will drive this from right to left. Okay, and at the same time, we can also look at it as if there are the negative charges, no? Analogously, will go towards the direction opposite F1 here because there are negative charges. So in a span of a very quick time, there will be a positive charge accumulation on one end of our wire and a negative charge accumulation on the other, such that there will be an electric field due to this charge accumulation, and that now we call it as electric field 2. Now, at a very small span of time, the magnitude of E1 will become equal to the magnitude of E2, such that the total electric field within the wire becomes 0. If there's no electric field here, okay, then immediately there'd be no current density. So in other words, wala na ring current. So current becomes 0 now kasi nga wala nang electric field that will somehow command the charges to move from one point to the other. And this happens very, very quickly. So in that case, current is not established kasi nga, it's not connected to a complete circuit. So if we want to establish current, okay, there has to be a source of uh, energy for the current to be established. So, and what is that? So now we go to the concept of an electromotive force. Although this we'll know in a while that even if this is called electromotive force, this is not a force, but it's actually energy per charge. No? So we need an electromotive force here to establish a steady current. To establish a steady current. Okay. So what do we mean by electromotive force? There is a device that can actually provide EMF, no? So that device, we call it an EMF source, EMF source. Okay, and the common EMF source that we have, of course, a power supply or battery. So we have batteries, we can have power supplies, solar cell, etc. Power supply, or let's say um, solar cells or solar panels, etc. Yan. So, what is common among these devices that enable them to be considered as EMF sources? So, here's the deal. Let's talk first about the most familiar EMF source to us, and it's a battery. Let's say a dry cell battery. So, if this is a dry cell battery, yan. So, let's say this is the positive terminal, the battery, and this is the negative. I'll call this positive as, let's just say, point A, and then this point here is point B. I think I've mentioned this in earlier videos, no? So an EMF source has the ability of uh, tawag nito, lifting, no? Lifting charges from low potential to high potential. That what makes it an EMF source. So what is this EMF? So say for example nga itong si battery natin. Now, if this is not connected to in to a circuit, so it's just so not connected to a circuit yet, connected to a closed circuit. Okay? So knowing that this is, let's say, the higher potential, the positive terminal, and this is of the lower potential, the negative terminal, then we learned that there is an electric force or the electric field here within the battery causes a charge, no? Say a conventional charge, to fall from high potential to low potential because that's natural for it. That's natural for this positive charge to get attracted to the negative terminal. But the explanation there is that since there's an electric field here, no, that is directed away from plus and towards minus, then this charge here is being acted by an electric force. Okay? Ayan. So, sooner or later, if this battery here has no mechanism of lifting the charge from low to high, okay, from low to high, then this cannot be considered as an EMF source. But what happens in a battery is that meron siyang mechanism that allows the presence of a non-electrostatic force. So let me just erase this for a while. Ayan. Let's focus on the forces. So again, because of this electric field here from plus to minus, there is a downward force here that is electric. But the battery, since it is an EMF source, it has the capacity to exert a electrostatic force on the charge so that this non-electrostatic charge will somehow my dogs are barking. Okay. Let me stop the recording for a while. Let me pause it for a while. Okay, the dogs are quiet now. So let's continue our chikahan. Ayan, where was I? Okay. So, saan na tayo? So the battery itself, since it is an EMF source, it has the ability to lift the charge from low to high potential. Most of the physics books, we often refer to this as the water pump analogy. No? Water pump analogy. Yan. And then other physics book would also have a charge escalator. Charge escalator. To somehow give us a picture, no? A more familiar picture of what happens inside an EMF source. So what is a water pump analogy in the charge escalator? You think of an EMF source as if it's a water pump, okay? So you know what a water pump is. You have a fountain, for example. So let's say it's a fountain. Paano ba ang fountain? Yan. Okay. Yan. So there's water here. And then naturally, water would fall from high to low. Tama ba? Yan, hulog ang water dyan. Without the pump, if all of the water from this point has already fallen on the lower ground, then it cannot go up by itself. But with the water pump, then it's being pumped uphill. And then the cycle of the falling, the fountain water continues. So parang ganun ang EMF source. Meron siyang capacity na i-lift yung charges from low to high potential. Kung dry cell siya, yung source ng non-electrostatic force is coming from a chemical reaction within the solution. I think I've mentioned this really talaga, no? In the earlier videos. So when all of the chemical reactions have taken place, then the non-electrostatic force vanishes, and the only force that will be present is the electric force. And then very quickly, the electric force will cause these charges to fall from high to low until such point that the potential in A is already equal to the potential in B. So there's no more difference in potential. Kaya nga ito yung sinabi ko before na drain na yung battery mo. Diba? Drain na siya. Yan. So in other words, what's common in the three kinds of EMF sources here is the mechanism of providing non-electric force so that the charge will be carried from the low to high, opposite to what happens by nature that it falls from high to low. Okay? Ito na yung external force na sinasabi natin last time. Every time you defy what's natural, you have to do external work, additional work. So parang ganyan siya. Okay? So the same concept with charge escalator. Parang ganyan yung ginawa ng isang author, di ba? So from negative terminal to positive terminal, it's as if there's an escalator of charge, no? So that the charge would go from low going to high. So what happens now if it's not connected to a closed circuit? We say here that the magnitude of the electric force is just equal to the magnitude of the non-electric force. So if you add the two forces along the y, it's zero. There's no net force. Therefore, there's no net motion of charges, something like that. So if there's no net motion of the charges, then the positive terminal will remain positive. The negative terminal will remain negative. So that in imuhang battery, your battery will always have a potential difference. Because this potential difference, remember, this provides energy per charge. So if you connect now your battery to a closed circuit, this energy now will be transmitted all throughout your circuit. Kaya if there's no difference, there is no energy. So in other words, if we connect this, however, so if the battery now is connected to a complete circuit, connected to a complete circuit, pardon my writing class, complete circuit. So this is what happens now. Okay, what do you think? How do you compare electric force this time to non-electric force if the battery now is connected to a complete circuit? So this was our battery. The positive terminal will say it at higher potential CA, lower potential CB, negative. And then let's connect this to our wire. And let's just say there's a resistor here, R. Yan. And then let's draw another, oops. Yan. So that I can draw the charges. So what happens now, I'm still using conventional current, ha? Please take note. Pag conventional current, we are uh, looking at positive charges as the one that are moving. But in the actual circuit, positive ions in the wire cannot move. It's the electrons that are actually the charge carriers. But since the conventional charges natin have equal charge with electron, if let's say there are three positive charges moving clockwise, it's equivalent to three electrons moving counterclockwise. So it will produce the same current. Ayan. So it's just a matter of perspective. So we have, for conventional current, it comes out from the positive terminal. So this is high potential. Yan, high potential. The positive charges now will go from, so if there are charges passing through the wire here per time, then that's current. So we have current in this direction for the horizontal segment. And then we have vertical here, current. And then the same current passes through R because this is just a simple series circuit, I. And then it enters again the battery here. So as a charge comes out from the positive terminal here, it has high potential. Whatever is the potential here at the positive terminal, that's also the potential of the charge as it comes out. However, so let's just say the wire is ideal wire, so that the resistance of the wire is taken as 0. So the only resistance in the outer circuit here is due to the resistor here, itong si R. Okay? Yan. So as the charges come out here and as they pass through the 0 resistance wire, then there is no change in the potential yet. However, as the charge now passes through this resistor, they will be rubbing, of course, with the ions of the resistor, causing it to heat up. Okay, so there be a decrease in the potential here, so that ganito siya class. If you know the direction of the current as it passes through a resistor, always remember that the potential of the charge will always drop. Okay? So, let's just say, for example, na pagpasok niya dito, I suggest you put immediately a positive sign in this end of your resistor. So, that refers to high potential. But as it enters and passes through the resistor, it will lose potential. No? Energy per charge. It will lose energy per charge here. So that when it comes out sa resistor natin dito, lalabas siya ngayong mas may maliit na potential. Ayan. Until, since there is only one resistor here, external resistor, whatever is the, tawag nito, the terminal voltage of our battery here, that will also be the voltage across the resistor natin dito. I'll discuss it in detail in a little while. Yan. So, in other words, the charges have high potential paglabas sa positive, but it will always have a potential drop every time it passes through a resistance, whether the resistance is due to a resistor or whether the resistance is due to the wire. Kasi ang real wire, meron talagang maliit na resistance yan. So a potential drop every time it passes through a resistance. Yan. So paglabas niya dito sa negative, it will now have a less potential. If we take this potential here as 0 volt, then all of the potential that it has, paglabas niya sa positive here, no, yung energy per charge na meron tayo dito, it is somehow lost because of the heating of the resistor here, such that paglabas niya dito, it will now have 0 potential. Ayan. So, once it now has 0 potential here, kasi na-convert na nga yung energy per charge natin, the charges now cannot go by itself from low to high here inside the battery. But since battery is an EMF source, it has the ability to move the charge uphill. So the charge now will have a potential rise. Yan. So meron tayong potential rise. Every time the charge enters the other end of the battery, it gets charged up again. So if it has 0 potential at this point here, it will now gain another potential so that the cycle continues. So when does the cycle of the movement stop? Meaning, kailan mag-stop ang kuryente? That is if there is no more supply of non-electrostatic force. Okay? Pag wala ng supply ng non-electrostatic force, the charges cannot be pumped uphill anymore. So, meaning nga, battery is already drained. Okay? So, I hope you got it. You got the idea there. So, in other words, for an EMF source, okay, every time the charge enters an EMF source, the charge undergoes potential rise. Okay? Although, pag meron ng another battery na nakakonect dito, tapos it is what we call series opposing, meron na namang a little difference. No? But in general, charges will have a potential rise every time they enter an EMF source. So it's actually the EMF source that provides energy per charge. Okay? Kaya EMF, electromotive force, is not a force. It's energy per charge. So its unit is still joules per coulomb, which is still volts. Okay? Ayan. So, I hope that's clearer now. Yan. So we have two kinds of EMF sources. Number one, we have the ideal EMF source. And for an ideal EMF source, it has 0 internal resistance. So small letter R, that's for internal resistance. Ayan. In reality, there's no such thing as 0 internal resistance for our batteries. Excuse me. And then, of course, we have the real EMF source. So, the real EMF source, the internal resistance is not 0. If your battery is good, no, it's still new, hindi siya old stock, then the internal resistance ranges from 0 to around 2 ohms. So, malalaman nyo na internal resistance yan. The resistance is low. Now, there are cases when you buy batteries, no? Bago siya, pero madali siyang madrain, no? It means that the internal resistance of the battery has gone up. And that usually happens if it is stored for a long time. Even if it's not used, the internal resistance increases with time. So if you will know, no, na the battery is old stock kung bago pa siya, and then when you have your voltmeter, if the battery says it's 9 volts in the packaging, tapos if you connect it to your voltmeter, I hope you know how to connect the voltmeter, no? It has to be across. So if this is the plus, this is also the positive of your voltmeter, negative, negative. If the reading here in the voltmeter is very much less than 9 volts, okay? If the terminal, so let's say this is point A, point B. So in this case, uh, the potential difference between A and B, that will be the reading in the voltmeter here. If this is way much less than 9 volt, then you know that the internal resistance of the battery is very high. Meaning, luma na yan. Matagal na yan tinago ng nagbebenta. Yan. But ideally, uh, for an ideal EMF source, so, ang battery natin ngayon, pag ideal siya, ay, bakit siya naging parallelogram? Ayan. For an ideal battery, if, by the way, the voltage label in the battery, that's the EMF, okay, that the battery is claiming to offer. So for a real, an ideal EMF, if, tawag nito, the terminal voltage of an ideal EMF, so meaning pag i-connect natin to sa voltmeter natin, hindi pa siya connected sa circuit natin. Since the internal resistance is 0, so ang symbol natin ngayon is ganito. So if you want this to be the positive, then you draw here a longer line, short, long, short. It doesn't matter ilang pairs. And then no internal resistance sa loob. So it means that the R here is 0. So whatever is the EMF of this battery, this will also be the terminal voltage of the battery here. Ayan. Hindi pa natin siya kinonect sa closed circuit ha, kasi pinakita natin dito, it's just connected to a voltmeter. We're just measuring the terminal voltage. When we say terminal voltage, it's the voltage across the terminals of your element. Terminal voltage. And take note, see terminal voltage, it doesn't have to be always V sub AB. Kasi depende yan kung how we label the points across the battery. Because there are cases na, let's say there are several batteries in the circuit, and then this point here is labeled as C, and this point here is labeled as D, then the terminal voltage here is labeled as V sub D. Tapos, you have to be careful in writing the subscripts here because the order will tell us the polarity that you are, the order of the polarity. So, see VCD here, although it has the same magnitude with VDC, but since C is of higher potential and DC and D is of low potential, if let's say the EMF here is 3 volts, then the potential at C with respect to D should be positive 3 volts, saying that the first subscript is of higher potential than the second. So if we get the potential at D with respect to C, since D is of lower potential, na siya sa negative terminal dire, then we have to put here a negative sign, 3 volts. The negative sign here is telling us that the first point that is labeled here is of lower potential than the second. Okay, I hope that is clearer. And then, forgive me if I'm talking very fast. Anyway, you can always pause and then replay whichever part of the video. Okay, my bias is that I want to explain several concepts in a short span of time. So you can always review whatever is not clear. Ayan. So at this point, we are comparing ideal EMF with the real EMF source. Let us continue. So the second point here, let us connect the EMF sources now to a complete circuit. So that's case number 3. So again, we can also position the battery horizontal, of course. So let's do that. So, by the way, I'm sorry, dito pala sa real EMF source. So we will label this now inside. So we draw the rectangle for the casing of the battery. And then since this one is the positive terminal here, let's connect this to a longer line, short, and then plus, minus, and then a tiny symbol for internal resistance, which is still the zigzag, the usual symbol for resistance. Ting, 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 ting. Yeah. So this is now the resistance, internal resistance of our battery here. So if you're given a circuit, if there is no interior resistance inside the battery here, that is somehow telling you that that battery is ideal. Okay? So let's connect our ideal battery, for example, horizontally. If I want the left side to be of higher potential, then I can just sketch it long, short, and then no zigzag thingy inside. Yan. So let me label this as point A, positive, point B as negative, and then I'll connect it to an external resistor, for example. Say, dalawang resistors in series. I'll call this resistor 1, call this resistor 2. So, in this case now, uh, uh, yeah, we are still using conventional current. So immediately, you locate where the positive terminal of your battery is. And remember that conventional current comes out from that. So from high potential, it falls to low potential. That's the way to look at it so that you won't be confused. So immediately you know that for this simple series circuit, this is ideal EMF, there's no internal resistance. You can remind yourself that R is 0 here. So you have a counterclockwise direction of the conventional current. So as the current passes here, it's somewhat downward. And when it goes to this segment of the wire, the same current passes through R1. So from this point, since you know that every time current passes through or a charge passes through a resistor, it will have a potential drop. So immediately you put the high potential symbol here and then low potential. We have to practice as early as now because we are preparing for Kirchhoff's laws. No? Ayan. I really want us to reach Kirchhoff's so that somehow you'll have at least the basic knowledge and skills when you go to your higher electric circuit analysis, whatever. Yan. So plus, minus, and then same current here, plus, minus, potential drop, potential drop. It has lost potential now, so that the charges now need to be pumped uphill again. So the charge now will go from low to high. That's the current now passing through your battery. Unlike sa earlier example, dito, there's still zero current, no? Because this is just a voltmeter. Mini-measure lang natin yung terminal voltage ng battery dito. So in this case, for an ideal battery, if there's no current passing through it, then immediately the terminal voltage VAB, or whatever symbol we have for the subscript here, is equal to the EMF. And the EMF, that's in the label of the battery nga, diba? The energy per charge. So that's one thing to remember. Ideal batteries, if there's no current passing through it, EMF is equal to VAB. But in the same thing happens if you connect it this time to a complete circuit, even if there is now current that enters the battery, but knowing that the battery has no internal resistance, so there will be no potential drop inside the battery. So what is the implication kung walang potential drop sa loob ng battery? The implication will be the terminal voltage of the battery, kahit may kuryente na that passes through it, will still be equal to the EMF of the battery. Why? Because this is ideal. There's no potential drop inside the battery. But if we connect a real battery, so if I will erase this, Gagawin ko siyang real battery, real EMF, such that the R is no longer 0. So I will put here a tiny resistance, R, so that this is now a real EMF source. Okay, so what happens now, as the charges enter the battery, it encounters resistance inside the battery. So there will be a little drop in the potential. So lalagyan natin dito di plus, minus. So what happens now, if we put a voltmeter here across the battery, symbol for voltmeter is V, yan. The reading that we will have here will be the terminal voltage of the battery, isn't it? Okay. Now, because there's a potential drop inside, the this is for ideal. Because there's internal resistance now, the reading in the voltmeter here will be less than the EMF label of the battery. Kasi nga, merong potential drop because of the internal resistance. Specifically, the terminal voltage of our real battery this time will become the EMF, no, the reading in the battery, minus the potential drop in the small r here. So the potential drop is just given by Ohm's law. So you know that voltage equals I to current, so that the potential drop in the small r will be current through the battery times the small r. So this I times r, this is now the potential drop of the charge inside the battery. It will be subtracted from the EMF of the battery. So, ito na siya ngayon, small r. Ayan. So, this is for real battery or real EMF. Okay? That is why for real battery, sabi ko dito kanina, when you have your battery, you measure the terminal voltage, do not expect na the voltage label is equal to the actual terminal voltage. If it says 9 volts and if the battery is good, the terminal voltage is it's less than 9. So it's usually 8.9, 8.8, 8.5 depende sa R niya. That's for the real battery. But if it's very less compared to EMF, yun na nga, the idea there is baka luma na yung battery mo. Okay? Ayan. So, what else do we have here? So from this, we can actually determine now the current. I'm almost done in this video. Okay. We can determine the current that's flowing in our circuit here. Okay, so how do we do that? We just have here, so for IR, sorry, yan. Asa na ako? Saan na tayo? Okay, so, next. If we get the, so ito dito, this is potential drop, excuse me. And this is another potential drop just given by Ohm's law, diba? So the potential drop across resistor 1 is just IR1. And then the potential drop across R2 is just IR2. Remember, in my discussion on series circuit, the total voltage of your EMF source is distributed or divided into the resistors here. Yeah. So we can actually say that the total voltage here, VAB, is just equal to EMF. So if we take this now as total, we'd say that EMF minus the I resistance total. So in other words, we say that we can actually take this as one, no? So in this particular case, you have EMF minus I, and then you have the internal resistance R plus the R1 external, R2. At saka, depende na yan kung ilan sila sa buong loop dyan. And then the VAB here, am I making sense? Yeah. Okay. So, saan na tayo? Nawala ako sa line of thought ko. Sana ako? Bigla akong nawala. Sige, wait. Let me pause for a while. Ayan, let's continue. Okay, saan na tayo? Ayan, let me have a little correction here. So, ayan, sorry guys. Ayan. Ayan na yan. So we say that the the terminal voltage across the battery is equal to the total voltage across the external resistance. So that is given by Ohm's law, right? So we have here I, and let's just take capital R for a while as the total external resistance. Okay. R is the total external resistance. Okay, so do not include the internal resistance of the battery. So on the left-hand side, this is now equal to this one. Yan. The EMF of the battery minus the potential drop inside the battery is equal to the potential drop across the external resistance. We want to get an equation for I, current in the circuit here, so that we say that EMF is equal to I external R plus I internal R. And then we say that I is just external plus internal, and then the EMF. So that EMF over total resistance, external plus internal, will give us the current in our circuit. Yan. So we can easily determine the current there. Okay? Ayan. So that's the difference. I think I have to stop here. No? So let's wrap things up. Important points in this video. Number one, that for established current to be, for a steady current to be established, okay, so steady current to be established within your circuit, there has to be an EMF source. See, the EMF source, what's the ability of the EMF source? It moves the charge. It has the ability, it has the mechanism to provide non-electric force. So it moves the charge from low potential, that's from the negative terminal of your source, to the high potential. Because the reason for this is the provision of the non-electric force. The source of the non-electric force depends on the kind of EMF source. What I have just discussed with you are for dry cells. So for dry cells, you have there the chemical reaction of the solution, no? Chemical reactions there. Yan. For solar cells, for power supplies, they have another mechanism for that. Yan. What's the other important point that we learned here? For an EMF, in general, in an EMF device, what happens to the charges are potential rise, or they have a gain in their potential. Yan. And for any resistance, the charges will undergo a potential drop. So if potential rise is from negative to positive, potential drop is from high to low. Okay. And then finally, we have two kinds of EMF source. We have the ideal EMF sources. Okay. Wherein with or without current, the terminal voltage is equal to the EMF of the battery. And for real EMF sources, without current, the potential is equal to the terminal voltage, I mean, is equal to the EMF. Yan. Okay. But this is only for tawag nito. Yeah. Ay, sala. Wait. Did I miss something? Okay. This is for real, no? Sige na lang. So, for a very good real batteries where we consider R as approximately 0, then pag walang current, the terminal voltage is equal to E. But if there is current passing through the battery, we'd say that the terminal voltage is EMF minus the potential drop inside. Kaya pag walang current, if this is 0, yan, this is 0, this is true. Okay, take note of that. Ayan. So, yung sinabi ko kanina dito, okay, na sa totoong ito, for example, there's still very small difference, no? So, if it's say, usually it's, let's say, approximately 8.99 volts. So, we can still approximate it as 9 volts, something like that. Yeah. And then, the last one, I think that would be the last one. So these concepts are very important when you analyze circuits later. Okay, I'll stop here for a while and see you in the next video.